an approach that most of the technologies follow, not only geothermal, of course, but I tried to scale it down to the geothermal applications for the purpose of this presentation. And I will briefly show some case studies at the end. And if we have time, I plan to do a demonstration of the NREL System Advisor model's geothermal TEA options. So having said that, so as I explained, I will briefly talk about the TEA, the techno-economic analysis methodology, and I will mention 3 tools that we use very often: GeoFires, System Advisor model, and the annual technology baseline. And I will just give some examples of some case studies, geothermal and solar thermal case studies, and conclude this presentation with key takeaways. So as an introduction, this is the Techno-Economic Analysis 101. Techno-Economic Analysis, shortly TEA, is a method for evaluating the economic performance of the technology. And the TEA assesses the overall value of the technology, allowing analysts to objectively weigh benefits of the cost. And it is an integrated process and cost model which combines the elements of design and modeling, plant sizing, capital cost estimations, operational cost estimations, and also financial analysis. So these are the main 5 components of a TEA. So when you start an analysis, definitely you need to know what you are modeling. When it comes to design and modeling, are you modeling a power plant, or are you modeling a direct heat application? If it is a power plant, are you modeling a hydrothermal system or an EGS system? Is it a flash cycle power plant, binary cycle power plant? And your resource availability, of course, not as like a big conceptual model, but the TEA recent tools integrated some subsurface modeling into the analysis as well, such as GeoFires and System Advisor model has that capability of modeling the subsurface. And after that, when we come to the surface, of course, what will be the size of your plant, the plant efficiencies. So the more you know, actually, you have a better TEA analysis. Then comes the money part of it. What's the cost of these things? You should have a good understanding of your bill of materials, component by component, and also some cost estimates for the engineering, procurement, and construction. And of course, the soft costs such as permitting, licensing, or leasing, those kind of soft costs are also important. Then, of course, operational costs are basically any maintenance cost, energy and labor costs during the production stage, and replacement parts when needed. And the financial analysis actually includes, main component of the financial analysis is the discounted cash flow, which is a cash flow that represents the annual revenue through the power plant or the facility you are building. So having said that, so this is the basic TEA flow chart that NREL's System Advisor model is using. So as you can see here, we have the weather data because this is the resource in terms of solar DNI for solar PV and CSP plants. In our case, in geothermal, this is the resource. We can replace this with that. Then system specs, the resource data, and system losses comes to the first box, which is the performance modeling. So we need to model the system to get the hourly production, annual hourly production, which will give us the capacity of the plant during the operation times. In geothermal, we are lucky that it can be 24/7. In solar, of course, it is fluctuating throughout the day, sunny days more, and peak times of the day during the noon hours are the more productive hours, and nighttime is almost coming down to zero. But geothermal doesn't have that fluctuation. It's a constant production. Then after we had the production, of course, the cost comes into play. The better estimate we have in cost model will give us a better financial model. Then other things which are hidden but very important can be a game changer. The incentives, like the state, federal tax incentives and other kind of support, and financing model or financing options is also the key. When you model some project, it can be 100% equity, but a financing percentage may make the project more feasible, and the interest rates are coming into play. And it's a key part of the techno-economic analysis. Of course, compensation is also important. And at the end, when we have this cash flow, our important outputs are the levelized cost of electricity, net present value, payback periods, and the revenue and savings. It can be revenue or savings, and taxes. As a whole, at the end, we have a dollar value of the project, and this could be this should be actually parameter that is comparable to other technologies, because at the end of the TEA analysis, the main purpose is to compare. So this is the time you evaluate the project, and you're not trying to build a full financial model for your project. You're trying to compare options and find the best option before you start the project. For that reason, this is a value that is comparable. So having said that, we talked about these output parameters. The levelized cost of electricity or levelized cost of heat is the price at which the electricity is generated and sold at a certain price, and the system is at the break-even point at the end of its lifetime. Discounted cash flow is the revenue or the valuation of the revenue as a throughout the lifetime of the project, that gives future cash flows during the whole project period. And net present value is the value of after-tax cash flow, this cash flow in 1 year, normalized to the project year. And internal rate of return is very similar to net present value, but it is the time when the net present value becomes zero. And of course, the final thing is the payback period, which is the simplest, but more important than maybe any of them, because at the end of the TEA, the operators or developers wants to see when the project will pay itself back. How many years will it take to get their first initial investments back from the project? So there are a couple of slides which has some formulas. The first one is going to be the LCOE or LCOH. So technically, as I explained, this is the sum of the capital cost during the installation of the plant, plus the O&M cost throughout the lifetime of the plant, minus, this is the optional part, if there's a secondary revenue. If this is a combined heat and power plant and there's a revenue from heat as additional revenue, which will kind of help the O&Ms get less and less, this part is subtracted from the operational costs throughout the lifetime of the plant. With D is the discount rate here, the discount rate applied again throughout the lifetime of the project. And the denominator here is the sum of the energy produced, also discounted with the discount rate throughout the lifetime. And this value is usually in dollars per megawatt hour or dollars per MMBTU. And when we have this number, we can literally compare two different projects. Which has the highest LCOH is going to be more expensive. The lowest LCOH is going to be more feasible. And the other way of calculating the LCOH is a fixed charge rate. In this one, this is simpler. And the reason why I explained both of them, you may not need to apply the discount rates for calculating LCOH. You may just get rid of that and just apply the fixed charge rate to the total cost of the system plus the fixed operational cost divided by the annual generation. And if you have a variable operational cost, which in geothermal we usually don't, it's usually set as zero, but in PVs or battery systems, there might be some variable operational cost. If there's any variable operational cost, you add it extra to that. As you can see, this is a very simple calculation, but sometimes it works better than the discounted, what is it called? Discount rate application, the normalized way of doing it, for simplicity, and also if you are not very sure about the financing options of the project. The second important financial parameter is the net present value, and also the internal rate of return is a function of net present value. The discounted cash flow DCF formula is equal to the sum of the cash flow in each period divided by 1 plus the discount rate, which is also called as weighted average cost of capital, VACC, raised to the power to the period number. And net present value actually deducts that initial capital cost from this formula. So up to here, this formula is the DCF. And when you deduct the capital cost investment from here, which is actually cash flow every year, coming from your revenue divided by that discount rate throughout the lifetime, minus the initial capital investment, gives you the net present value. So what does it mean? So net present value can be positive or negative. If it is negative, that means you are losing money by the end of the project. If it is positive, that means this creates a value added, and the bigger numbers are making the project more feasible and better compared to others. What if the net present value is zero? Then it becomes, that's the point of the internal rate of return, the IRR, which is calculated using the same concept as the net present value, but it is the point where net present value is equal to zero, which is actually representing the percentage of your investment coming back to you every year. The final and the most simple approach is the payback period when you evaluate a project. This is basically dividing CapEx by the annual revenue minus the OpEx. And this gives you the number in how many years the project will pay itself back. And even though it's simple, it is very useful. You will see in examples when we talked about the demonstration and also the case studies. Apart from these variables, we have financial variables, which are very important for the TEA, such as the analysis period. It's going to be 25 years or 30 years. The project tax, income tax, state tax, sales tax, property tax, the salvage value of the system, the debt structure, such as debt percent, tenor, interest rate, closing cost, upfront fees. Those kind of debt-related numbers are important. Also, the construction financing, reserve accounts, even the depreciation. Sometimes we apply this, sometimes we don't. But if the parts and the components of the project, such as the plant components, depreciate throughout the lifetime of the project, we may apply a straight line or a makers, such as the modified accelerated cost recovery system, this depreciation schedule to the project. Also, incentives, investment tax credits, production tax credits are key. And finally, the power purchase agreement or power heat price that will create the revenue stream for the project. Okay, so this is the basic concept of the TEA. TEA has these components. So now I'm going to talk about tools that we can use for this. One of them is geofires. So originally built by MIT, and in 2018, NREL updated this tool by adding the reservoir well bore and surface parameters and surface plant technical models, cost correlations, and a detailed calculation of the LCOE, including the capital cost and the O&M cost of the project. And very recently, this year, they released the new version. It's called version 3, or they also call it version X, which included many other end-use options, not only electricity, but direct use heat, combined heat and power, absorption, chilling, cooling, and heat pump technologies. And also, for the very first time, the district heating option includes hourly heat load optimization and peak performance evaluation in geofires. So how does geofires look like? So there are the different user interfaces. It's built in Python and public and open source. You can download from a GitHub server and modify based on your needs, or you can use the web version, which is more basic. If you are using geofires for let's say more simple projects, web version may help. Otherwise, if you are an expert user, you can just use the Python version and modify the code based on your needs. So what does geofires do? Basically, you add some parameters such as your temperature gradient of the system, how many wells will be drilled, if wells will be drilled, how many wells will be drilled, what diameter, what will be the expected flow rate per well, and also what's the cost of your system, the capital cost, and what would you expect for the operational cost. So you basically enter whatever information you know. If you don't know the reservoir parameters such as permeability, porosity, you can start with the default, of course. And after that, geofires creates a generation profile and temperature thermal drawdown curves, as seen in this figure, throughout the lifetime of the power of the plant, which is 30 years here. It just shows the temperature drop in 30 years, flow rate changes, and also the changes in the pumping power. Those kind of technical parameters can be plotted. In addition to that, the annual generation can be plotted with respect to the project timeline. What's the heat extracted from the reservoir? What's the pressure drop in the reservoir? Those kind of technical parameters can be modeled with geofires. And this is the link. I think at the end of this presentation, I can share the slides. You can download geofires from GitHub. And this is the new version, geofires X. And if you are a Python user, you can just play with the code, modify things if you feel confident, and get some cool results. So this is the second tool I'm going to talk about, which is actually the most complicated and my favorite, NREL's System Advisor model. So System Advisor model is a free technology or free techno-economic analysis software for decision-making purposes. The current version is 2022 version, but the 2023 version is released for testing. If you want to just download and just play with it, it is available in NREL's System Advisor model webpage. You can download the most recent version and test it. So basically, what does this tool do? You can define your power plant, starting from your geothermal resource, plant and equipment configuration, power block, grid limits, installation costs, and there are more detailed costs in the model. Probably if we have time by the end of this presentation, we can do a live demo of SAM. And you can have a couple of options. You can use a hydrothermal or EGS system. When you have an EGS system, as you can see here, You can even add your fracture model, fracture spacing, length, aperture, width, angle, rock density. Any parameter related to reservoir can be added only in the EGS model. For the hydrothermal model, it basically takes a simple thermal drawdown reservoir model, not a detailed reservoir model. So you can put your estimated potential resource temperature, define your depth, expected depth where you want to drill. Those kind of features can be added. And this is new. You can do this for different types of plants, hydrothermal flash or binary EGS, both for near-term and deep EGS, binary and flash technologies. It can be a greenfield or brownfield. This will literally adjust the parameters and give you a better estimate of your LCOH and other financial parameters. So that was the resource part of it. The plant part is actually, you can define your technology. It can be a binary or flash cycle power plant. You can technically let the software calculate the plant output, or you can manually type exact output you want, like a 30 megawatt, 20 megawatt, or you can just say you will have this many wells, number of wells, 4 wells, and then our flow rate is this, our depth is this, our temperature gradient is this, and it calculates the production capacity of those 4 wells at that design temperature of in here is 200 degrees. It's hard coded. We can change it. And then, of course, if you know parameters such as the pumping parameters, okay, the flow rate is high here, 110 kilograms. You can change it. You can change your pump efficiencies, pressures, anything related to the well pumps can be added here. Then we come to the cost. Definitely, the exploration cost can be added in this section, and the drilling cost. This is new. This has changed last year. Now this estimates the drilling cost based on Sandia's 2018 or 17 report. I think it was 18 report, which has a very nice estimate of a well drilling cost for baseline, intermediate, and low and high scenarios. So you can literally change the diameter of the well, deviated, straight, or any kind of complicated drilling operations can be modeled, and the cost has been estimated based on that drilling parameters. After that, another cost component comes from the plant. So based on the output, you can, if you know a hard-coded baseline cost such as dollar per kilowatt, you can hard-code it, and it will basically multiply that number with the gross plant output. Or you can try to fine-tune it based on exact plant cost that you know, and it can be flexible. Of course, other pump and field gathering system costs can be added here. The pump cost or the casing costs. Then any other surface equipment costs can be added. Oops. And we can also add indirect capital costs such as labor or procurement, engineering, sales tax, as I explained. We can make this very, very detailed if needed. And after that, we sum everything up and we end up with a total installed cost here. In this example, it's almost $150,000 value. I mean, these are arbitrary numbers right now. When we model a real case, this is going to be more realistic. Of course, you can add a contingency. You can change the percentage of the contingency here. And after that, that comes to the financing model. This is the trickiest part because you can play with it. It can be a 100% equity project. You can just put a debt fraction of 0% and make this a 100% out-of-pocket project, or you can add a debt fraction such as 60% of the capital cost or something. And the loan period can be 20 years, 15 years, and you can add the inflation rate. If you use the fixed charge rate method, FCR method, as I explained in the equations, you can define your FCR percentage here, then it calculates that in the LCOE calculations. So the options are endless here in the financial parameters. You can add anything you want and make this more detailed. And at the end, this is basically the results that you see. The results of the system advisor model gives you the annual generation, the plant's capacity factor. In this case, this is super high. It may not be this high in real case. We need to fine tune that. The PPA, you set this PPA, it's $8 per kilowatt hour, and it calculates you the LCOE. In this example, it's 709 cents per kilowatt hour. That means this is a good project. You are making money from every kilowatt hour you generate. If the LCOE is higher than the PPA, that means you're losing money, which is not a good project. And net present value is positive $35 million, which is good. Rate of return is 56%, which is very high, not very realistic. There might be some tricks that we need to play. That means in 2 years, less than 2 years, project pays itself back. This is not very common. We usually expect like a 10 to 15% IRR in a real project. And net capital cost is almost $150 million. Now we use a debt percentage a normalized debt percentage of 75% of the project is using financing. So having said that, you can also see your annual energy generation and the drop in the lifetime. You start with the high profile, and at the end of the project lifetime, you can see the total drop in net electricity generation because of the thermal drawdown in the reservoir. You can also see monthly generation fluctuations based on system kind of noise. We call them noise, but the system electricity consumptions from generation. So when we come to the demo version, we can basically have a roundtable discussion, and we can literally have a live demo, play with these numbers, and see the effect of these changes in the project when we come to the end of this presentation. I will keep this for later. So last thing I want to mention about the tools is the annual technology baseline. So this is slightly different than the other tools. This is not a project level techno-economic analysis. This is like a technology level techno-economic analysis. So in this tool, this is a web tool. You can create graphics and download the Excel spreadsheet and just change your numbers and try to create your own curves. This is actually calculating the LCOE within the projections. That means it adds the fourth dimension to your LCOE calculation. This is taking your project to future. It just forecasts if your project is established in 2030, what would the LCOE be based on the learning rate that the technology prices drop, and your financing gets better, you get additional tax incentives and etc. So this is basically how it looks like. So same thing, we calculate the LCOE with the FCR method. In here, we add other things such as the ITC, PTC schedules and so on. And if you look at this LCOE, this is today. Your project is here at this $30 per megawatt hour level, or $33 megawatt hour. Let's say this is 2030. If the same project is built in 2030 with the learning rate, these are conservative, moderate, and advanced improvements in the technology. The expected LCOE will be less in advanced scenario. So every scenario has different components. Of course, improvements in drilling technologies, faster, cheaper drilling, and so on. If you follow the conservative technology, the expected drop in LCOE will be this much, as you can see here. And if you follow the advanced scenario, the expected drop in LCOE would be this much. So this is a useful tool to compare What if my project is built 5 years later, based on that learning rate? How cheap would it be? So having said that, this is an example. So we talked about those conservative, moderate, and advanced scenarios here, and this is the near field EGS. So if you look at the capital cost, it's high in today's technology. If the business as usual continues, the blue line, it will not be cheaper much. But if we can continue with the moderate and advanced scenario with some advanced improvements, now the technology would be cheaper throughout the years with the learning rate. Especially this is good example for EGS. So we don't have this kind of big drop for hydrothermal systems, but for EGS systems, we can just see by 2030, we can at least have 1/3 of what we have today in terms of the EGS systems. If the advanced scenario, we should look at the definitions online. There's a big list of definitions. If the advanced scenario comes into play, it can be 1/3. But if the business as usual scenario continues, the drop is not that significant. So also you can see in ATB, the historical fluctuations in LCOE, starting from last 10 years, 12 years. It's actually fluctuating. And this is for, this time not for EGS. This graph is for hydrothermal flash. And you can see how the LCOE can fluctuate even for a certain technology in terms of dollars per kilowatt hour. And this is the expectation for future based on the learning rate. And you can do the same thing for different technologies for hydrothermal flash binary, near field EGS and flash and binary, and deep EGS flash and binary. So after this, let's talk about some case studies. Our first case study is a geothermal power plant turbine case study with custom and standard design. This was designed for a 5 megawatt system. And now in this, this is the link for the NREL report for this project. I put all the web links. When you have the presentation, you can find the technical report for those. So this is comparing two different designs of turbines, a custom design and a standard design. And we have the LCOE calculation. And as you can see, the custom design is slightly more expensive than the standard design turbine. And in terms of the net present value of the standard design turbine is higher than the custom design turbine. Of course, the IRR is higher, which is, I was explaining this, 12% is expected. That means every year the project pays its 12% back in roughly, let's say 6-7 years, the project will pay its price back at this rate. So having said that, we also looked at the net present value. So we saw that the net present value is positive, which is good, but it's not always positive. So there's a boundary. So this is a good exercise to take a look at how the net present value of my project changes if my resource fluctuates. As an example here, if I have this is the flow rate in terms of kilograms per second. If I have, let's say, 2 wells, two of them are flowing with 40 kilograms per second in a total of 80 kilograms per second, and my temperature is 170 degrees, I'm here. So my net present value is positive 1.5 million and above. So I'm good. What if my flow rate goes from 80 to 60? Then I'm at the limit of the economic boundary. So I'm still at positive, but my flow rate is not that high. If my flow rate goes slightly more, I'm in negative zone. So technically, any flow rates around 58 kilograms per second at the same temperature makes my project infeasible because it's negative net present value. So this is a good exercise to compare where you are, and that gives you an idea of what would be my flow rate be at that temperature, or can I have a jump to from 70 to 75? Then this can take me to the positive section or positive zone of the project, that my project still can be at the positive net present value. Another important project was a project for absorption chilling for turbine inlet cooling. So this is an example of how detailed the cost can be or should be. If you have more detailed numbers here, even if you have a retrofit to an existing system, if you know your cost precisely, this will give you a better understanding of your capital cost and operational cost. And in this case, we have two plants. We are comparing two plants. One is a retrofit, the other one is a brand new plant. And the brand new plant is cheaper than the retrofit. It's a $32 million project. This is a $26 million project. And then we look at that, the LCOH. So this is the graph for the LCOH versus the payback period. The LCOH can be exactly the same in both projects, around, let's say, $3.8 per MMBTU, which is very close to the natural gas price. Looks very promising. But if you look at the payback period, because of these high costs here, in here, the payback period is like almost 40 years. That means the project pays itself back, maybe almost 45 years, my bad. The project pays itself back by 45 years, which no one wants to build that project. But if you take that project to a merchant plant example, that you can lower that 45 years payback period time down to maybe 16 years, which is also high. But that's a big difference. So this is showing us the importance of payback period, because even though LCOH seems very promising, the payback periods may not be as good as LCOH. Having said that, so this is also extrapolating this curve. That was an interesting project, assuming that the geothermal is free. They give you geothermal for free. Even at that level, this blue curve says the payback period is still very high. That means the surface equipment, that $32 million, is extremely high, and it never pays itself back properly based on that rate. And for this one, even lower, but this assumes the LCOH is 0. That means geothermal is free. Even if they give the geothermal power or heat for free, there's like a six years of payback time for that $26 million upfront cost. And also, this was a 100% equity project. There was no project financing here. I should mention this. So this is a good example of importance of simple payback period, even though it seems like very simple, just divides two numbers, but it is important. Another thing, this is actually related to our project, which we described in GRC this year. The district heating project, it's a heating and cooling project we modeled. We modeled 4 different scenarios with like a duplet and quartet models using TOF2 simulator, using the GeoFire's built-in TOF2 simulator. And we tried to calculate the LCOH for these scenarios. And we found out that the duplet model with 1 production and 1 injection well was giving a good LCOH, a better LCOH than others. And it had the least thermal drawdown in the production scenario for 30 years of production. Also gave us the highest utilization factor. So these results actually are updated after the conference. We used a different approach. We just changed the injection temperatures and we just changed some parameters. But this was a good approach that at least we were able to see as an initial insight that the quartet model with 2 production or 2 production, 2 injections, or 3 production, 1 injection was not the best way of doing it. And we thought that 1 production, 1 injection would give us better results based on the proximity of wells in the area. And in terms of the utilization factor, that is the highest of all. So that was a good practice for that purpose. So last one is a solar thermal system. I love this project because this is a hybrid project. This has the solar thermal linear Fresnel collectors here with a combined phase change material storage tank and a natural gas backup for industrial process heat applications. And as you can see, solar thermal is very dependent to DNI in the different geographic locations. That changes a lot of things. Also, the other thing is the natural gas price in different locations. Like California natural gas price is high, Pennsylvania is higher, Arizona is cheap. Even though Arizona has the highest solar resource, it has the cheapest natural gas. And when we compare the standalone natural gas boiler system with respect to a hybrid solar thermal system, we can see the least solar DNI value in Pennsylvania give us almost equal LCOH with respect to a natural gas boiler system because of increasing or adding some share with the solar component and offsetting some natural gas. And as the natural gas is the highest, that makes this project very competitive. And one of the things is the carbon dioxide emissions or tax credits. When you add the tax credits, which Pennsylvania doesn't have it at the moment, but California does, that can make a project more feasible than a standalone project with the carbon adders. That also gives us the idea about how tax incentives are important for a project's techno-economic analysis. So key takeaways. We talked about the different components of TEA. The most important thing is it's a valuable tool for ensuring that the innovations are ready for market, from concept to market. And we understand the feasibility of the project by comparing the TEA or the outputs of TEA with other projects, and it gives us the flexibility to compare different technologies in terms of their LCOH or their plant efficiencies, their capital costs, etc. And the TEA can be better if we have a better understanding of the system design, if we know our costs better, such as CapEx and OpEx, if we understand our financial model and come up with a better financial model, and of course, if we have the benefits and incentives, as I explained in the last example, if we have this information, we can have a more accurate TEA. So that's the end. Thank you for your attention. And for the rest of the time, I would like to just show you a live demo and maybe open to questions.
Okay. Okay. Thank you. Thank you, Sertac. Very nice.
Thanks, Azar. So let me pull up that. So this is the System Advisor model. And this is the new version. When you download from this page, if we go back to here, so basically you go to this page, and this is the beta version. The full version will be available by the end of this month. You can test the beta version, or you can look at last year's version, which is very similar, but beta version is more up to date. You can maybe try both. You have to register with your email, and they send you a key. It's free, public. You can use it on your computers. After you download, this is going to be the user interface. When you start this project, you will see there will be a lot of technology options in the PVs, energy storage, hybrid systems, CSPs, etc., process heat, and that this is the one we are going to work on today, the geothermal module. And in here, after you take the technology, you need to pick your financial model. If you don't know anything about your finances, if you just want to model a technical system without an LCOH, you can easily select the no financial model. You can basically select, if you don't know much about the power purchase agreements and the cash flow, the discounted cash flow analysis, you can select a simple LCOH calculator, which is the FCR method, as I explained. But if you are an expert user, if you want to do a power purchase agreement, you can select, which I will do that today, a single owner power purchase agreement project, which you are very confident about your PPAs and interest rates and all financial parameters. That'll be the expert user. I'm going to start with this, and you click OK. Your project comes. And the first thing, actually, since SAM is being used for PV and solar technologies, the ambient conditions are important for them. For us, unless we are using air-cooled system, this may not be very important. But location, you have to pick your location from here. I'm just going to select maybe Nevada for this purpose. It's going to be dry climate, because I will just select air-cooled system. If you don't see your area here, basically you can go to this NREL weather files system, and you can put your coordinates, especially in Oklahoma, whatever you want. You can pull up that weather data to your project. This is just an example, but you can increase the number of locations. For now, for simplicity, I'm using Nevada example. Okay, then the first thing is the resource. Here you can select hydrothermal or EGS. If you select hydrothermal, your reservoir parameters, you can't play with them much. You have to just put your pressure drawdown and a temperature drawdown. And injection well pressure change. You can only change these two. But if you want to do an EGS, then it allows you to modify everything. Let's see. Okay, it's over here. Calculate. So it allows you to add anything, like the rock density, thermal conductivity, fracture geometry. You can add the complexity as much as possible, but this is only available for the EGS, not for hydrothermal, unfortunately. Of course, you can add your total resource potential, target temperature, resource depth. Am I drilling to 2,000 meter or 3,000 meter? And then you can, okay, this is the important thing. You can pick your system. Greenfield hydrothermal flash binary, Greenfield EGS flash binary, Greenfield improvement hydrothermal flash binary, and continues. So there are different options. In this case, I'm going to do binary, Greenfield reference binary. It's giving me a warning. It will overwrite other results. Okay, and I'm going to hydrothermal because it doesn't allow me to do this, because I have to select EGS binary. Then I can use these functions. If I click to hydrothermal binary, probably it will kick me back to this. Yeah, it's just kicking me back. It disables these kinds. I will just use a simple pressure drawdown. Then other tab is plant and equipment. So we can specify the output. This is a 40 megawatt plant. Let's keep it as it is. Or I can just say, hey, I don't know the exact output. I only have 4 wells. Then it calculates. I don't know the exact output. I have 4 wells flowing at 50 kilograms per second. And it calculates my capacity. And for this one, this is not flash. This is going to be binary system. What else we can change? If we know the ambient temperature, ambient pressure, we can change it. I'm not touching these at the moment. That's all for plant configuration. Then we come to the power block. I don't usually touch this. I use the Adams approach, and this is for cooling. We can, okay, this is important. We can select hybrid cooling, water cooling, evaporative, or air cooled. I will pick air cooled because it's in Nevada. We don't need water cooled. Okay, I'm gonna select the air cooled system, and I'm not gonna touch the others for now. Grid limits, I usually don't touch this. I'm not a grid expert. And that comes to the cost. So in here, it's a very detailed cost model. I'm not going to change anything, but the one thing that is, you can have a PPI multiplier. If you know that your numbers are coming from a certain year, certain project year, you can select this. I'm not going to activate this at the moment, but you can escalate your cost. If this is like a 5-year-old cost that you know, you can just escalate this by the multiplier. And you can also select different cost curves, mid, low, and high, different cost diameters, deviated vertical hole, large diameter, small diameter wells. This will technically, if you select small diameter, probably this will update this curve. If this is a deviated with a liner, this will slightly change. So I'm going to say large and vertical at the moment with a baseline. So it just shifts from here to here. Baseline is expensive. So technically, if I want to get my cost low, maybe I should just go to the ideal. It will take me to the lower end of the cost, which actually changes my drilling cost. High cost drilling, low cost drilling, or something in the middle somewhere. Let's keep it as it is. And this one too, let's make it intermediate too. Then plant capital cost. As I explained, if you know your plant cost accurately, you can just say, hey, my binary plant is $1,800 per kilowatt, and this is my gross output based on that 4 wells that I put. It just multiplies these, and this is my plant cost. Then comes the pump efficiency. If I know pump costs, I can add that here. I'm not going to touch this at the moment because we don't know. And then indirect capital costs can be here. Indirect costs are such as additional taxes, engineering procurement, land acquisition, and any other miscellaneous costs that you want to add. You can add it here. Then it brings me to the operational cost. So for the operational cost, as you can see, this has $175 per kilowatt per kilowatt per year. If you know your O&M, you can type it here. Usually the variable O&M, like VOC, is usually 0 for geothermal. And if you know your annual cost, instead of this, you can put 0 here, and you can just actually type, I have $1 million costs annually. You can do that. Or coming back to that, 175. This is dollar per kilowatt. And after that comes the financial parameters. In here, you put your analysis period, 30 years, your inflation rate, discount rate, your PPA should also be somewhere here. It's in revenue. Okay. So you add the sales tax. If there's a salvage value right now, we say 0. There's no salvage value after the end of the project year. Then the debt structure. Okay. You can use a debt structure, or you can set your debt percentage. You can allow the software to calculate your best debt percentage, or you can say, okay, I'm going to just finance 50% of my project and 50% equity out of pocket. With 18 years of debt structure with an annual interest of 4. If you think that this is too low with today's inflation, you can increase it to 5. Let's keep it 4 for now. If you know the debt closing costs, upfront fees, you can add that here. If you know the construction financing, which we don't know at the moment, you can just say, hey, the percent of loan is 40% of it is pre-proof, which is the drilling and subsurface. 60% is on the surface, power plant and equipment. If you know this percentage, you can add that detail. Then if you know the depreciation schedule, you can add 5 years of makers, or you can say straight line depreciation. I'm gonna keep it as it is for now. And then comes revenue. If you know your PPA price, you add it here. If you have an escalation for PPA, you can put 1 or you can put 0. Let's say no escalation for 20 years of lifetime, 20 years of target lifetime, yeah. And that if there's incentives like ITC or PTC, you add it here. I'm not adding any incentive right now, no incentives. Depreciation schedules are here. As I explained, we are doing these federal and state level depreciations. If there's any additional purchases, no, we don't want that. And then we simulate. There we go. Now, after we simulate, we found that, okay, this is, we modeled a very bad system. Our PPA is $8 per kilowatt hour. Our LCOE is 8.67. That means we are losing money on this project for every kilowatt hour we generated. So we go back and change something, such as I increase my flow rate from 50 to 60 and run again. Now I am good because my PPA is $8. My levelized cost is, okay, slightly high, but the normalized one is getting better. We can just change it more. Go back here and make it 70 kilograms per well. Simulate one more time. As you can see, my LCOE improved. And if I just go back, make it 80, and simulate. Now I'm making money. My PPA is $8 per kilowatt hour. My LCOE is 7.98. So, I mean, I just played with the flow rate, but you can play with a lot of things. You can play with your temperature, other criteria. And at the end, that's your comparison. Your net present value is positive. You're good. Rate of return is 14%. Very good. You're making some money, not so much, but you're not negative. So yeah, and your debt percentage is, where was it? So your total cost is $120 million. We set 50%, $62 million out of pocket, $62 million financed. You can change your structure. You can just go back. Hey, I want to finance more. I want this project 75% financed. And now you run it. Oops, it's too much. It gives me an error. You go back to your financial parameters. Okay, maybe 60%. Makes sense. Now it's 60% financed. And my LC, this is a funny fact that as long as you finance more, now you have a better LCOE, 7.72 compared to 8. So yeah, the options are endless. I would recommend you to download this System Advisor model and play with it. Don't be afraid of making mistakes. Play and learn type of tool. And it has very good default estimates. Even if you don't know anything about geothermal, you click on random things. If you make a mistake, it gives you the error message and you just go back and fix it.
Okay.
Is there a way to save it?
Yes. Is there a way to save it?
Yes, you save this as a project.
Oh, okay.
Oh, yes.
Or you can create your data tables here, send it to Excel.
Okay, that's perfect.
So now we can
So you technically, this is the output. After you that, you put your, let's say, that's a good point. I should mention this. Monthly data, or let's say hourly data. Where's the hourly data? It's on. Okay, PPA monthly. Let's say monthly data for all. I'm just showing an example. This is the data. Let's say probably that's a bad data, but we can click on send to Excel. Actually, this was a better one. You can click on all of them and then send to Excel. Wait a minute. Everything is here. So this table came to Excel. You can export your data to Excel, or you can just save your project. Save as SAM file, test project. Yeah. This project. Save. And then let's say you closed it and you want to open a new project. Sorry, you want to open a project. Your test project is here. You can open and your project comes back. Every time when the project comes back, it doesn't come with the results. You have to simulate again. Oops. There's something wrong. This is, revenue is too high. Okay. So it probably made an error while doing something. But every time project comes back, you have to simulate again. We have to just do not save this. No, don't save it. Open a project file. Let's see. Let's open it again. All right, everything looks good. Yeah, that was an error. No, this is now working. So when you save it, you can go back and run it and play with it.
Okay.
That's all I want to say today. I hope it was helpful. I would strongly recommend you to download SAM and just play with it.
We will. We are going to do that. Definitely. Thank you so much. Okay, this is a very nice tool. Actually, is more powerful than expected. Thank you for introducing us to these tools. So, I don't know, guys, if you have any questions. Or let's see.
Can you hear me from here? No, I don't.
Now, I think that you have to go closer.
Oh, there's a seat for you.
Thank you. Sertac, thank you. It was a very good presentation. This SAM seems superior. At least the beta version seems superior compared to Geospheres. I really like the visuals and the interface is really nice. But my question's about overall payback periods for these projects. I know I'm gonna lasso all the projects in a big pool, but you mentioned I think 10 to 15% IRR, if I remember correctly, was general. So is that applying that 7 to 10 years payback? Is that kind of a rule of thumb for the industry? That's my first question. And then second question is, do you model this? The economics, are they more similar to oil and gas where accelerated revenue up front is your priority? Or is it more like, I know you have a PPA in there, but is it more like public utility where you lock in something for a really long time and just ride it out, and then you do a rate hike in 20 years or something like that? Is that kind of the model? Those are my two questions. Thank you.
Good questions. Thank you. Thanks so much. The first question, yeah. So this is based on my personal experience. I can just say not 10 years, but 6 to 7 years of payback period is usually expected from the industry. But 10 years, so literally with a 15% rate, you can get you can have a payback period of like 6-7 years. If it is 10%, it's 10 years, which is like anything below 10% is not very good. Like 12% is, there's no rule of thumb. It's not written in stone. Like, but usually 6 to 7 years of payback period is expected by the developers. Second question, that's a very good question. Actually, it is based on your PPA. If you have a good PPA, instead of that $8 per kilowatt hour, if you're lucky and you get this $10 per kilowatt hour for 10 years, you want to force the reservoir and just front load the project and just generate as much as possible with the high PPA when your PPA ends and when your next agreement is going to be less than that, or if you have a feed-in tariff, which is actually I'm originally from Turkey, and there was a legislation that they were giving 13.2 cents feed-in tariff with the domestic component supply. Okay, 10.5 cents plus up to 3 cents per kilowatt hour additional with domestic components in the projects. Let's say 10.5 cents. That was a great number at that time, but that was only for 10 years. And people just wanted the benefit from it. That's a business model. Good thing is you make more money in the first 10 years. Bad thing, if you don't have a good reservoir model, you never know what your temperature thermal drawdown will be after 10 years. You're taking risk by front loading the reservoir. So the short answer is yes, it's possible. It's a business model. You can make it, but you have to be careful about your reservoir pressure drops and thermal drawdown.
Thank you. Yeah, that is a very good point. Okay.
All right. Thank you all.
Oh, okay. There is another question.
Hello, Dr. Akar. Good afternoon. Good to see you again.
Hi there.
It's Kurban Hassanov talking to you. And my question is, you mentioned about drilling costs, amount optimum and like average or something. And my question is it like a fixed thing, or what is the formula behind it? Or can we include our model to that, or it's like a fixed? So what is the
there's a formula.
computational
This is
thing
from
behind it?
this is from the Sandia's report. I didn't put the link there. It's a technical report published by Sandia National Lab in 2018. So there are formulas for those, and I think I don't.
Can we change them, or they are
here?
fixed?
Sorry.
Can we change those graphs? I mean, like, can we include our own formula?
Not in SAM, unless you know Python coding and you want to be a part of the SAM team. Not in SAM, but these formulas are public in the Sandia report. You can get the equations. If you want to use at your own Excel or Python code on your Excel tool, or you want to use it on your Python code or whatever, I can add that link to the presentation, the Sandia report. There will be a link for the PDF. You can get the equations for all scenarios, large diameter, small diameter. So yeah, these are taken from the Sandia National Labs drilling cost report.
Okay, Sertac, at that point, is it possible to use a multiplier? There is an option to have a multiplier, you know, for adjust to a value that we think that is good, you know, instead of, you know, for make it easier.
Yeah. So this is actually just a visualization. I mean, technically, this is just helping you. Okay, hey, I have this well. Okay, I'm at 2,000 meter. Like if you look at this, go back to the geothermal resource. Hey, if you want to drill to 3,000 meter and come back to installation cost, where is it? I'm still at 2,000 meter. What happened? 2,000. This is weird. Geothermal resource. 3,000 meters. It's resetting for some reason. Anyways, I have to fix that. That's the beta version. We have to change it. It's not updating it. So you have to put 3,000 meters.
Or probably save, you know.
Yeah, I don't know why this is not updating. No, still 2,000. That's weird. So it should change to 3. It changed. My bad. It changed. Okay. Now it's 3,000 meter, and you can just select the ideal case. This will drop this down here. And then this takes the cost. And you can just say, hey, I want the deviated liner formula changed slightly. I want small diameter You just shift it that little bit,
Yeah.
cheaper, or you can just, I mean, it gives you some options to move within these lines, and the equations for these lines are in the Sandia report.
Dr. Akar, thank you very much for your answer. But my question was exactly like, can we change those equations? Or, or
SAM?
it's like we have to be like a part of the generators for this program, like,
Not in SAM.
or probably,
If
for
you want
example,
to change
if
it for your purpose, you can change it, but you can't. This is not an open source coding.
yeah, that's what I wanted to know.
This is
Probably,
not
for
open
example,
source.
if we
Yeah.
have to wait for
I mean, yeah, you may suggest changes to the NREL team every year. They have a maintenance budget.
yeah,
If you feel like these curves are not good, you may suggest changes, but you can't change it in the public version.
yeah.
You can change it on your end for some other purpose, not on the public version.
All right. Thank you very much.
Yep. All right. So I have to head out to my next meeting, but thank you for your attention.
Absolutely. No, thank you so much for
Thank you,
taking this time. So I think that also we can contact you by email or something if you have any doubts, right?
Okay. Thank you.
Okay.
And it's
Okay.
nice.
Thank
Thanks.
you.
Bye-bye.
Thank you, Sertac. Okay.